Hello, I welcome you again to this series of video lectures on the use of CPN tools. This is video number 2 of Unit 3. We will be discussing the implementation of queues in CPN tools. In the last video, we discussed the implementation of time in CPN tools. In this video, we will have a closer look at the behavior of transitions when time delay is associated on them. We will look at different ways of implementing systems with time. A special type of color set called list color set plays a very important role when it comes to implementing queues in CPN tools. So we will start with an introduction to this color set and use it to implement a queuing behavior in a very simple CPN model. A list color set, here is an example definition of a list color set. What we have done over here is we have defined a color set job, J-O-B, with 3 colors or 3 elements in it. So the 3 elements are job 1, job 2, and job 3. The next thing we'll do is we will define a color set job list, which is of type list. It's a list of job. So what we will have in this set will be list of elements, where the elements would come from the color set job. Let me give you some examples of the elements that we may have in this color set. Here is an example. You see those square brackets. This is the syntax of a list in ML or CPN ML. So anything enclosed inside these 2 square brackets will be list of those things. What we have right now is just a single element in this list, and the element is job 1, because job list is a color set of type list, where the list has elements from the color set job. This is a very simple example. Let's see another example. Here is another example of a list element or a color from this color set. Now we have 2 elements in this list, job 1 and job 3. We may have as many elements as we like. We may have repetition of elements, so we may have 2 job 1s, 3 job 2s, and as many job 3s as we like. So there is no restriction that every element must appear at most once. As long as you take the elements from this color set job and add those elements to this list, this will be an element of this list color set. We also have a special element in this color set, and that is called the null list or nil list, NIL. It's an empty list. We also use this keyword NIL to represent it, but 2 square brackets with nothing between them is a list of no elements. It's still an element from this color set. It's a color in this color set, but it does not have any elements inside it. There are some operators which are also very important when it comes to list color sets. The two most important ones are head and tail operators. The head operator, for example, if we apply it to a list, we have a list with 3 elements, job 3, job 1, and job 1 in it. And when we apply this head operator to it, what we get is the first element from this list. So this operator, when applied to a list, returns the first element of that list. So here we see job 3 is the value returned when we applied this operator. The tail operator, on the other hand, removes this first element and returns the rest of the list back as the return value. So when we apply tail to the same list with 3 elements in it, job 3, job 1, job 1, it removes the first element, which is job 3, and returns the remaining list, which has these 2 elements, job 1 in it. There are some other things which are also very important. One of them is called this list construction constructor. It's not an operator, and we'll try to explain as to what is the difference between an operator and a constructor. So let's look at this constructor, which is shown as these 2 colons. So job 2 colons followed by a list. In our example, we have only 1 element in this list, but we can have as many elements in this list as we want. So it's a constructor where the left hand side has a single element, and the right hand side has the list of elements from the same data type or color set. When we do that, it's basically is a different way of representing. It's not the return value, it's just a different way of constructing or representing a list where job 2 is the first element and the rest of the elements come from the right hand side of this double colon constructor. Another example may help you understand this thing. Suppose that we have two variables, x and xs. X has job 2 in it. Xs is a variable of type list, and it has a list in it, job 1, job 3. When we construct this expression x double colon xs, what we are representing by doing it is this list where the first element of this list comes from the value that x has in it, and the remaining element of the list come from the list xs. In other words, if we have x double colon xs assigned this list job 2, job 1, two elements in it, then x gets the value job 2 and xs gets the value of the remaining list if you ignore the first element in that list. So it's a constructor, it's a way of representing a list in terms of its first element and the rest of the list when you remove the first element from it. So it's not an operator, it does not return. It assigns these values to these two variables x and xs if they are used in constructing or representing this list using this double colon operator. We will use it when we will go to the implementation of queues in CPN tools. It's very important that we understand this constructor because it will play a very important role in the implementation of queues. Similarly, we have this concatenation operator. It's an operator. It is used to construct a list from two argument lists. So we have the left hand side of this operator, a list, and the right hand side is also a list. It is represented as two hats. So concatenation is two hats right next to each other. It's an operator. It requires two arguments. Both should be of type list. So here what you see is an example where job 1, job 3, the left hand side is a list, the right hand side is also a list. When we apply this operator, the return value is the new list which combines the elements from these two lists in a single list. So the first two elements, job 1, job 3, come from the left hand side of the argument of this operator, and job 2 comes from the other right hand side list. We may have lists larger than these. For example, here is an example where we have two lists. The first one, job 1, job 3. The second one has job 1, job 2 as elements in that list. When we apply this concatenation operator, the return value is a new list with all the elements in that order put into this new list, and that is the return value of this concatenation operator. So with this quick definition and illustration of a list color set, we switch to CPN tools to see as to how we can use these things in an implementation of a queue in CPN tools. Our simple CPN model that we will use in this video to look into the timing behavior of this transition and the implementation of queues in CPN tools. So if you look at this Petri net, it has one single transition in the middle with one input place and an output place. Both these places have color set job assigned to them. Let me show you the definition of this color set job. If you look at it, here it is. It has three colors or three elements in it, job 1, job 2, job 3, and it's a timed color set which is described by this keyword timed at the end of this definition. Okay, we also have a variable j of this color set job, so we'll use this variable on the arcs in this Petri net model. So coming back to our CPN model, we have an input place to this transition. This transition is labeled server. It has a delay of 10 on it. So let's put some tokens in this input place and see what happens. So let me hit tab twice and then type some tokens and here are the tokens. Let me show you what I have put as tokens in it. So what I have is I have job 1 available at time 1. So the timestamp on this token job 1 is 1. Job 2 has a timestamp of 5. So job 2 will be available at time 5. And finally, I have a third token, job 3, which has a stamp of 7, which means that this job 3 token will be available at time 7. So what I've done is I've put 3 tokens. The first one will be available at time 1. The second will be available at time 5. The third one will be available at time 7. The transition has a delay of 10 on it. Let's see what happens when we run this Petrinet. So I rewinded it, and now this transition is shown enabled. If you go and look at the event clock or the simulation clock, you will notice that it says 1 as the time, and which means that there is something enabled at time 1. There was nothing enabled at time 0, and the reason for this time clock time to be 1 is this first token job 1 at 1, because this is the first token or the earliest time any token can enable this transition. Now when this token fires this transition, or this transition fires with this token, I'll fire it manually by clicking on this small green triangle at the bottom left hand side, and clicking it again will fire this transition. You see that the output token says job 1 at 11, because this token was available at time 1. It took 10 time units for this transition, which says server on it, to fire it. Therefore 1 plus 10, 11 is the timestamp at the output token. Let's see what happens again the next time this transition is enabled. We see that this transition is enabled. We go back to this clock and see what time is it. It says time 5, because this is the next time a token is available in the input place of this transition, which is job 2. Let's fire this transition again, and when we fire this transition, we see that the token stamp at this new token at the output is 15. It was enabled, this transition was enabled at time 5 with this token. It has a delay of 10, therefore 10 plus 5 became the timestamp on this token, 15. Similarly, we can again go back to this event clock and see what time is it now. It says time 7, because this is the stamp on the third token, and this is the next time this transition can fire with something. Firing this transition at time 7 will add a token at the output with the timestamp of 17, because 7 plus 10 is 17. So that's how the timestamps on the output tokens are calculated. Now suppose we wanted to model a physical server with this transition that processes one job at a time. When it processes a job, it takes 10 time units, and once it is done processing, only then it can take the next one. In our example, it would require that the transition representing this server should not take the second token until after time 11, when it is done processing the first one. We have just seen that this is not how our transition behaves in this example system. So how do we implement the situation that I just described? So in order to do that, let me first rewind this net and tell you as to how we do it. Let me take these to the other side. One modeling trick that people use to implement such situations is to add a self loop place to this transition. Let's just call it timer, and a self loop would mean that this place has both input and outputs to this transition. So we have we need a color set for this place. What I have done is I have declared a very simple color set E. It has just one element in it, small e, and it is timed. So I'll use this color set with this place. I'll give it this new color set E, and I'll also put a token in it, and this is just a single token E, which is available at time 0. So if I leave it as it is, it will add a stamp of 0 by default on it. So now I have a new place added to this system. I also need to add expressions. I'll use this expression small e, the constant, the element belonging to this set, on both input and output arcs. Now with this addition, let's now observe the timing behavior of this transition. Let me rewind it. And now if you look at the event clock, it says 1, which means that this transition is enabled with job 1. This is the token which is available at time 1. When I fire this transition with job 1, job 1 appears at the output with timestamp of 11. The transition is again enabled, but if you go to the event clock, it says 11 as the current time. In the previous example, it said time 5. Now it says 11. Look at the reason behind this jump from time 1 to time 11. When the transition fired, it updated the stamp on the output token, but it also updated the timestamp on the self loop in the self loop place. And if you look at this token over here, it says the same. It has the same timestamp 11 because the transition fired at time 1. The delay on this transition was 10. Therefore, 1 plus 10, 11 became the timestamp on this token. This transition now has 2 input places instead of 1 in the previous example. 1 incoming jobs, the previous old input, but it also has the self loop place as the input place too. In this situation, this transition will require tokens in both of these 2 places, input places, and it also needs to have tokens in those 2 places available before it can become enabled. If you look at the token which says job 2 at 5, this token will be available at time 5, but the token in the self loop place which says timer will not be available until time 11. Therefore, the next time this transition can be enabled is not 5, but will be 11, because time 11 is the earliest, is the next time when all its input places have available tokens. Therefore, this server, when it fires next time, it fires at time 11 instead of time 5. But now when I try to look at the bindings on this transition, it says that there are 2 possibilities. It can fire with job 2, the input token. It can also fire with the third token, which has a timestamp of 7. In the previous example, it fired only with job 2. So what has happened over here? What has happened is as follows. Since we have this new self loop place with a token that says 11, this transition is now enabled at time 11. But when the current time is 11, the tokens in the input places, both of them, since they have timestamps smaller than 11, therefore these tokens are, both of them are available now. Therefore, the second time this transition fires, it can fire with job 3. So I'm firing it with job 3 instead of job 2. And if you look at the time, the event clock time or the simulation clock time, it says 21 because it took 10 time units after time 11 for this transition to get the token in the self loop place enabled again. Therefore, this third time when this transition fires, it's time at 21. It fires at time 21 and adds the stamp of 31 on the output token and on the self loop token. So you may have noticed that with this self loop, we have implemented a server that takes 1 job at a time. If you have a capacity on this server, if it can take 2 jobs at a time, we can simply put 2 tokens in this self loop place and implement such a system. Notice, however, that the input place to this transition does not enforce any first in, first out scheme, as we have just observed with the case of job 2 and job 3 tokens. In other words, it is not a queue. It does not behave like a queue. So what about if we wanted to have a queue in front of this server?